You type one command. Immediately, an autonomous execution engine takes over. Without human input, it begins reading files, executing scripts, and writing code. Claude Code functions as an agentic harness built directly over your local execution environment. It operates with the same access to your file system, build tools, and Git state that you use during a manual session. The system operates on a continuous three-phase loop. Phase 1, gathering context. The agent reads files to understand the codebase. Next, taking action. It executes tools and modifies code to advance your goal. Finally, it verifies results by running tests and parsing error outputs. This loop is recursive. If a test fails during verification, the agent reads the error, gathers new context, and adjusts its approach. It can chain dozens of these actions together, course-correcting independently. But this autonomous cycle operates under a strict physical constraint, a 200,000 token context window. Every file read, a regex search, and command outputs consume this limited resource. Operating this agent effectively requires treating that context window as a strict economy. You must deliberately allocate tokens to memory, actions, and extensibility to prevent the system from exhausting its working memory. Before you enter your first prompt, the agent initializes. It surveys your local file system to establish the baseline for its operational environment. The architectural hub for this initialization is the hidden .claude directory. This directory serves as the central point for local state management and custom tooling. Inside is CLAUDE.md. This is your permanent, project-wide instruction file. The system injects these rules directly into the context window at the start of every session. Because it loads every session, CLAUDE.md should remain under 200 lines to prevent token bloat. Sitting directly on top of those instructions is auto memory. As the agent works, it saves cross-session learnings to prevent repeated mistakes. CLAUDE.md contains the manual, absolute constraints you define. Auto memory contains the system-generated patterns the agent picks up through observation. This initialization sequence ensures the agent operates using the same architectural assumptions and conventions as the engineering team. Properly configuring the .claude directory establishes the deterministic boundaries for the agent's entire execution loop. Once the session begins and the agent starts iterating, the 200,000 token limit depletes as the conversation history grows. Every action the agent takes, reading source files, running regex searches, and dumping terminal outputs, adds raw text volume to the session's active memory timeline. If this timeline overflows, the agent suffers from instruction amnesia, losing track of early constraints. To defend against this, auto-compaction is triggered. When the timeline hits the ceiling, a compression sweep crushes historical outputs into a condensed summary. The raw conversation history is summarized into a condensed format, freeing up space. But there is a critical exception. Claude.md and auto memory are immune to summarization. They are fully preserved and re-injected at the front of the new timeline. Conversely, rules scoped to specific file paths are lost during compaction. The agent will not recall them until it explicitly reads a matching file again. Custom workflows, known as skills, are also re-injected, but they operate under a strict volume cap. If a loaded skill exceeds its specific token budget, the system truncates the text to fit. Developers must anchor mission-critical operational rules in Claude.md because the context economy will ruthlessly overwrite any unprotected history. Adding custom workflows or external tool access introduces a new challenge, expanding capabilities without starving the core loop of available tokens. When you need to add on-demand knowledge or repeatable multi-step workflows, you use skills. Skills protect the token budget by deferring their load. The heavy markdown body remains outside the system until actively invoked. For actions requiring guaranteed execution, like running a linter, you use hooks. These execute in isolation, bypassing the token budget entirely. To block destructive commands, rely on a deterministic pre-tool use hook. To connect to external layers like databases, you use the Model Context Protocol. MCP servers defer their schemas until specifically requested. Choosing the wrong extension directly impacts agent performance. You must route capabilities through the correct architectural layer to preserve the context economy. Even with careful routing, massive tasks like deep code-based research or broad security audits will overwhelm your primary context window. To scale these high-volume tasks, you use the subagent architecture. This allows you to offload heavy processing into a state of strict context isolation. A subagent spins up in a pristine, empty context window. It reads hundreds of files without polluting your primary agent's memory. Once processing completes, it returns only a highly synthesized, low-token summary back to the main loop. In practice, this allows you to spin up parallel subagents to audit security flaws and verify performance regressions simultaneously without bloating the main session. Scaling agentic capabilities requires isolating the heavy lifting. Reserve the primary context window exclusively for high-level orchestration and final decision-making. Operating this system effectively requires the mindset of a lead systems engineer delegating to a complex architecture, rather than just prompting a chatbot. First, protect the baseline. Keep Claude.md concise and migrate heavy, repeatable workflows out to dynamic skills. Second, enforce system security and absolute guardrails through deterministic hooks, removing them from the model's reasoning cycle entirely. Third, defend the active context economy by offloading token-heavy research and parallel processing into isolated subagents. When state management, memory optimization, and extensibility are perfectly aligned, the system stops generating text and starts executing engineering work. Mastering these architectural layers transforms the terminal into a self-correcting environment that executes, verifies, and iterates without manual intervention.